We're going to start our week here looking at what's called polynomial long division. And to understand polynomial long division, it's probably best to start by making sure we really get the idea of long division generally. Where, remember, we've talked about division and ratios and fractions before and tried to give some context for why we care about them, where what we're doing is systematically breaking a thing, a number, down into smaller component parts. In particular, what we're doing is reversing multiplication. So if I, for example, want to divide 24 by 6, what I'm asking is how many times, or what do I multiply 6 by to get 24? Where in particular, you handle that sort of thing in this sort of way, and you'd get 4. Because 4 times 6 is 24. It's the reverse. It's the inverse in the same sort of way that we saw when we talked about inverses in the last chapter. And probably this didn't feel so nice when you were in elementary school, and it might still make you a little bit nervous looking at it now, but it's really not so bad. At least this one isn't. Maybe you get things with remainders, maybe you have much nastier numbers to deal with, but it is somewhat manageable, maybe not always easy. Because I guess if division was always easy, then Plato wouldn't have said, "He who can properly define and divide is to be considered a god." Where, in particular, we should understand that this construction, this little tableau thing that we have for division, isn't always how division was handled. In ancient Egypt, for example, division was performed using repeated powers of 2 along with the divisors. So you'd have, like, to divide something up by 7, you'd say, okay, multiply it by 2, then 4, then 8, and see how many you get in there. And then once you get close with a 7, you say another 7, that's your remainder. It does work. It is kind of clunky. It's systematic at the very least, but you got to know a lot of powers of 2. And that system kind of assumes you're only ever going to work with small numbers to begin with. And so you get big, you're really going to have to stretch the limits of your mental times table for that to work. And even though there were other ideas, this one wasn't one of the ones that stuck around, and a lot of those didn't either, where the one that gets closest to where we are, at least the one that starts hinting at our construction, is said to be the system put forth by the Persian mathematician Al-Khwarizmi. And I apologize if I butchered his name there. He frankly deserves a little bit more respect because his name is where the words algorithm and algebra come from, and for that matter, he's generally credited with having brought the Hindu-Arabic numeral system that we use today to Europe in the, I believe it was 9th century. But he was among the first to use what was also called the galley or scratch method, which is a little bit closer to what we have. Like I said, it's inching towards what we have here, unlike many of the other representations of that era, where the next along the line, the next closest to ours, would come from the Adanda Method, as shown by Calandri, which got brought to England through Henry Briggs at Gresham College in 1597. And to be fair, with all of these different ways of handling it, with these different mechanical approaches, these different algorithms, as it were, division actually wasn't considered an elementary school topic. It wasn't something that a lot of mathematicians in the 16th century would learn, at least not in Europe, until they were at about the age you guys are, until they were in university. And thinking about that, it kind of gives some perspective. It kind of makes at least me wonder what it is that we're learning here that in 400 or 500 years people will look at and think is so elementary that 10-year-olds should be learning that instead of 20-year-olds, or what they'll be learning as far as math goes at all at that point, because we will probably all be long gone by that point. But it's a lot of history, it's a lot of context, a lot of suppositions that aren't necessarily my place to be worried about. For us, what we should be focused on here is, again, understanding that when we're talking about division, even though it's not always a simple thing, even though it's something that took a while to get to where we are now, we're just talking about breaking a thing into parts. We can extend this idea of breaking a thing into parts using what is called polynomial long division, which is a very appropriate name because it's long division on polynomials. It's how you break something down into pieces of x's instead of just numbers. It's the exact same idea, as we'll see, it's just there's a little bit more tinkering that has to be done. Where another way that we can think about the idea of division, in this case maybe going from 24 by 4, or still 24 by 6, actually goes either way, is saying that we want to remove a 4 or a 6 or whatever from that factorization, be left with whatever we have there. If we remove a 6, we'd get a 4. If we remove a 4, we'd have a 6. And if we have a factor with polynomial long division, it works in exactly the same way, as we'll see. And that's something that we are particularly interested in, where when we deal with something like x cubed plus x squared minus 1, we have a process like so, where we arrange the divisor and dividend, the thing we are dividing and the thing we are dividing by, in descending order of their powers of x. We divide the first term of the dividend by the first term of the divisor, which gives the first term of the quotient. Multiply every term of the divisor by the first term of the quotient. Subtract that product. Bring down the next term of the dividend. Add it to the remainder from the previous step. And repeat these steps until we are either left with something of smaller degree than the divisor or 0. Where if we get 0, that means we actually just have a factor. So let's look here at an example for how this thing looks, because it probably sounds very intense in terms of that process. But we'll see it's, again, basically the same as dealing with long division, just got some more unknowns.